E205 literature review. Just as a reminder, my final project is enhancing GPS localization in urban settings. The paper that I found that was related to this topic is titled Augmented Kalman Filter and Map Matching for 3D RISS/GPS Integration for Land Vehicles. A couple things to note. This RISS stands for Reduced Inertial Sensor System, and you can think of that like just an IMU. Another thing to note is that this paper is catered towards cars, so not humans. So it isn't a perfect kind of alignment or corollary to my project. The paper's main motivation is to make position estimation algorithms more robust in environments where GPS is intermittently blocked by using a known map to correct for small errors in estimation, in position estimation as shown in the pictures above. This is a block diagram of the Kalman filter portion of the algorithm proposed by the paper. On the left is the sensor input from the GPS as well as the IMU. You'll note that they also use the odometer measurements from the car itself, so they kind of access the wheel's current velocity. I'm not going to go into too much detail about this because, again, this Kalman filter is something that we're more familiar with. This is, on the left here, is the Kalman filter implementation proposed in the paper, and as you can see, it's nearly identical to the one that we've learned in class. So again, I'm not going to talk about it too much. One interesting thing to note is that the state that they're working on, this X kind of hat, is actually a state error. So it's not an actual state, it's the difference between two states. And you'll notice this if we look back on the previous slide. The input to this Kalman filter is the difference between the state estimated by the GPS and the state estimated by the RISS. But as you can see, the algorithm is basically exactly the same, but just an interesting thing to note. For the rest of the presentation, I'll be talking about this map matching block in green, which is really the novel algorithm proposed by the paper. The proposed algorithm takes the output of the Kalman filter based RISS and GPS filter and returns a new estimated position that is matched to a nearby location on a known map. Before the algorithm can be run, the map data needs to be formatted in a particular way. First, the GPS coordinates at various locations along the road lengths, called nodes, are translated to a Cartesian plane using the familiar equirectangular projection above here. The paper did some fancy stuff where they accounted for the differences between the meridian and normal radius of the Earth, but I'm not going to deal with that in my algorithm. Next, a table like the one here is populated with the slope and intercept in the Cartesian plane of all the line segments connecting adjacent nodes on the same road. Depending on the size of the map, this table can be quite large. Once we have the map data formatted correctly, the map matching algorithm can be run. The algorithm has 5 steps, and I'll go over each of these steps in more detail in the following slides. The first step is to pick out all the line segments that are within some radius of the estimated position of the vehicle. This makes the algorithm faster because the next steps do not need to perform calculations on as many line segments. Step 2 is the azimuth or heading or yaw threshold check. This basically throws out the line segments that aren't aligned close enough to the car's estimated heading for the algorithm. And the threshold proposed by the paper is 40 degrees. So this is the estimated position. This arrow here is the estimated heading. As you can see, any of these line segments that don't really align with this arrow are thrown out or ignored. Step 3 is to ensure the perpendicular projection from the estimated location, again this is this black dot, to the line segments intersects the line segments between the two nodes. So we have 2 paths here, or 2 line segments, or 2 road segments, and then this dotted line, or these dotted lines, are the perpendicular projection. In the case of segment 1, this projection intersects between the 2 nodes. In the case of segment 2, it doesn't. So we end up throwing out any of the roads where that perpendicular projection doesn't intersect between the 2 nodes, and this further narrows down our list of potential streets. In step 4, the equation shown here is used to determine which of the remaining line segments is closest to the estimated location. As you can see on the block here, in the diagram here, we've ignored these other 2 line segments and selected this one road segment as the most likely candidate for where the vehicle actually is. Then finally, the intersection between the nearest road segment and the perpendicular projection is calculated and returned as the map matched position estimate. The experimentation conducted by the team who wrote this paper was pretty straightforward. They put all the sensors in the back of a van and drove around Kingston, Ontario, which is apparently Prof. Clark's old stomping grounds. At various points during their trial, they simulated a 60-second GPS failure and compared the error associated with the common filter-based algorithm to the error associated with the same algorithm augmented with the map matching algorithm. A military-grade GPS and IMU unit, the G2 ProPack span, was used for estimating the absolute truth. One of these trials the team conducted was in a largely urban area. The path here is shown on the map in red. All of the locations where the GPS outages were simulated are numbered. The plot on the right shows that in all cases, the map matching augmented algorithm resulted in a smaller maximum position error during these GPS outages. Zooming in on one of these simulated GPS outages, we can see why. The red line is absolute truth. The green line is the estimated position only using the cheap RISS, and the blue line is with the addition of the map matching algorithm. Without the map matching algorithm, sensor drift causes the position estimate to slowly kind of diverge from the actual position until the GPS signal is regained, and then you see it jump back to the actual position here. So the map matching algorithm presented in this paper is very applicable to my project. However, the other algorithms proposed by the paper are less applicable. GPS watches don't have useful or like reduced inertial sensor systems. They do have IMUs, but they're not affixed to a rigid body like a car, so it's hard to use their outputs. In addition, the motion model for a car is very different from that of a walker or runner, so I need to take that into account. Just a brief update on what the progress I've made so far. I've finally been able to kind of parse information from a map file. So all these white lines are known like street locations, and then the blue line is during a kind of test trial of the GPS output for a walk. All right, any questions?